delivers research through investors, indicators, and thought leadership pieces. Megan co-authored various works works closely with institutional investors. Megan graduated summa cum laude at Bentley University with a BS in finance and economics. Thank you. Take it away.
Yeah, and everyone was virtual. So the topic tonight is relevance. The main idea is that this is a way of improving forecasting. So this concept of relevance is work that I've been doing with our system and these years. That's the idea. So as I mentioned, so I guess just to set the stage a little bit, the idea is that we develop a framework that helps improve the reliability of forecasting. And when we think about forecasting, we think of
hard to hear.
Thinking of that we have in mind. So if we were to just take a step back a little bit and think about forecasting a little bit existentially, it's all about forming our view of the unknown. We do that naturally all the time when we're making decisions. But the way that we process decisions and process experiences can be a little different whether we're doing it in a natural setting.
We can't hear you.
Yeah. Okay, I can come closer. Yeah.
Yeah.
Okay. Cool.
We can't hear you.
Okay. Can you hear me now?
Yes.
Better.
Okay. Cool. So I can just start over a little bit. So this is a topic that's about improving forecasting using a concept called relevance. And so I was just setting the stage a little bit with some motivation, which is just contrasting the way that we tend to process information, whether we're doing something more in a natural setting or more of a statistical setting. So on the natural side, we tend to record our experiences as narratives or memories. We tend to focus on past experiences that are similar to the experience that we're currently trying to process. And then we also tend to focus on more unusual experiences. They tend to be a little bit more informative. On the scientific or statistical side, we do things a little bit differently. So when we record our experience with data, when we try and extract from that data, we tend to use as many observations as we can, so that we get more reliable prediction if you have more observations that are underlying it. And then the other, when it comes to outliers, we tend to do them with skepticism, right? So we tend to be concerned that outliers may overly influence our predictions, and so we tend to maybe examine that through the lens on our data. So if you look at these two processes, they're kind of in conflict with each other. And so the kind of spirit of our framework is to look to improve forecasting by essentially recognizing something we call relevance. So what I'll do is I'll first introduce relevance conceptually and mathematically. Then I'll relate relevance to regressions and event studies, and then talk about how we can use that to improve these forecasting techniques. And then I'll quickly summarize and also touch on some interesting extensions at the end. So let's start by talking about relevance. And for this, I'll actually ask that you'll kind of want to reorient your perspective on the lessons a little bit. So rather than focusing on the variables themselves, we want to focus in our framework on the observations. So rather than asking, how important are these variables to my prediction, which is the answer by looking at regression. Instead, what we're interested in is how important is each observation in my prediction. And that's what we measure, and that's what we measure by looking at relevance. So the idea is that we have a set of circumstances for today, and let's assume we want to predict today. And what we want to do is we want to know how relevant is each historical observation to today. And we do that by comparing the X variables to the predictors from past observations to today, well as past observations to kind of average circumstances. And those two components make up the two components of relevance, which are similarity and informativeness. So that's the kind of the overall framework. So again, relevance is based on the X variables themselves. But again, we're not interested in how important is each variable to my prediction, but rather how important is each observation to my prediction, and that's informed by comparing the variables from the past observations. So this definition of relevance, and I'll show this some math in a little bit. This is not arbitrary, so it actually follows from an equivalence of linear regression. So this definition of relevance is tied to linear regression. And then from there, we'll show how you can actually improve this new perspective. So,
question.
Yeah.
So when you're observation, so I mean, obviously the extreme observations can be very influential on statistical calculations. But when I think what you're implying is that somehow then you can be extra relevant.
yeah, exactly. Yeah. So we interpret that as they're more informative. I'll actually talk about that. Exactly.
Informative,
Yes.
okay.
Yep. Yeah. So the two components of relevance, similarity and informativeness. So the first one, similarity, is pretty intuitive. The idea is that we're looking at past observations that are more similar to today's circumstances. They're going to be more relevant to predicting today. So this is something that we tend to implicitly do when we tend to or overweight more recent data points and look back in those regressions. The difference here, though, is that's a pretty ad hoc way of discerning similarity based on the recency of the data. So we're going to take a statistical approach to measure the similarity between observations and say in a more objective way. So what we deem as similar may end up being data points that are more recent, but it's also observations from the distant past that just happen to be relevant. So that's the first component of similarity, of relevance and similarity, and again, when it's pretty intuitive, and then it's more similar to that, should be more relevant to today's observation, prediction. The second piece of relevance is informativeness. So this is what we were just talking about. And so this one, to your point, might at first seem less intuitive because we tend to want to dampen outliers in our data. But from this perspective, outliers or extreme observations are actually more informative. And so then this is, of course, assuming valid data and not erroneous. The true observations that are more extreme can be this actually relates to perspective relates to information theory. The information theory says that information is universally. Okay. Just said, yeah. Sorry about that. What do I look like on this camera? Let me just. Okay. Well, I don't know if I'm. What? Thumbs up. Okay. Okay. So I apologize. I don't know what I'm doing. So basically, relevance. Relevance tells you about the importance of an observation to a prediction. It depends on the X variables or the independent variables of the observation. There's two components to relevance. There's similarity and informative. So the idea is we're looking at a historical observation, comparing it to today to determine its similarity, and then we also compare it to average conditions to determine its informativeness. So informativeness, which we're on now, is related to information theory. So again, the idea being that more unusual or information is inversely related to probability. So a less likely outcome actually contains more information. A nice intuitive I think example of this would be if you had 10 friends and knock them all number 1 through 10, and then to add them together and then tell you the result. If the result was 100, you would know for certain what everyone picked. Everyone had to pick a 10. There's only one way that would happen, so there's a lot of information in that outcome. But if the answer was 50, which could happen millions of different ways, you would have to really know clear way of knowing. So the idea being that the less likely outcomes tend to contain more information. So from an observation perspective, this translates to more extreme outcomes tend to be more informative. And I think the intuition here is that more extreme observations are less likely to be accidental. So they're more likely to tell you more information about the true structure of a relationship than if you're focusing on an observation that's kind of average, and there could be just more that's driving that relationship, and that relationship. So that's the second component, informativeness. Again, the idea being more extreme observations are more informative, and therefore they're also more relevant.
That's got to be an assumption about the measurement of that, you know, in any observation has a band around it. If you use information theory, that's certainty associated with it. And probably the more unusual, bigger bands are.
Yeah.
So you got to balance those things out, right?
Yeah, so we measure it very precisely with the Mahalanabis Distance.
Oh,
So we'll
our
talk about that.
favorite.
Yeah, I'm sure you guys have seen that from some of the other stuff from us and from our over the years.
Oh,
So
okay,
we're
right.
huge fans of the Mahalanabis Distance. So that presents a lot.
Some frequently works off of the Informativeness systems we have from the natural language processing perspective. The sense that, the more frequent it doesn't mean like, it's important, but some unique terms.
Yeah, I guess it would be exactly that, yeah. Right, yeah, I mean, the more unusual something is, the more informative it is, the more I guess meaningful it is, the more important. Could be, but I mean, information there, closet together.
Right.
I mean,
Right, but that's the theory. With the reality, speaking of stream observation, and the first thing I think is measure error.
well, yeah, so this is presuming that it's not a measurement error.
Like,
So I would not
Oh,
suggest overweighting an
It's in
error.
my head a can opener.
Yeah.
Alright.
So of course, yes, this is assuming it's valid. So,
Okay, all right.
yeah,
Please.
if you think it's a real number, I would suggest removing it. So, okay, so those are the two components conceptually. In terms of measurement, that's what we're starting to get at. So when we talk about informativeness and similarity and relevance overall, these are multivariate concepts. So, right, so we're looking at conditions that are being, every observation we're assuming is being described by a number of different variables. And we've been using the term attributes a lot rather than variables to talk to X variables. It kind of helps reinforce this observation perspective and move away from focusing on the variables themselves. So I'm going to try and say attributes. So anyway, so we're characterizing observations by multiple attributes. So when we compare two observations, we care not only about the differences in attributes in isolation, but also the differences in the interactions of the attributes or the co-occurrence of the attributes all at once. So for example, if I'm comparing two observations that are being defined as growth and inflation, I care not only about the differences in the two growth rates and the two inflation rates, but also the differences in the combination of growth and inflation between those two observations. So that's an important point, and that's where the Mahalanabis Distance comes in. Because we're going to measure these concepts using the Mahalanabis Distance, and this is useful for our purposes because it considers correlations and variances of the attributes. So what that means is when I'm comparing two data points, unlike the liquidity that we're talking about, the differences in their attributes individually or in isolation, this is also going to tell me the patterns of those between those attributes different between the two variables. Very powerful and informative. So an observation, for example, could be unusual, not because it has really extreme values for the attributes, it could be because the co-occurrence of those attributes is very unusual compared to typical.
So it's not the observation, it's the observation in the context of more other features that go along with it.
Yeah, so
That's
we're
what
gonna
makes it unusual.
so what we're going to do is we're going to compare, and I'll show this in a minute. So what we do is we're going to use the Mahalanabis Distance two ways. We're going to use it to compare two observations, so a past observation to today, and that'll be, you're right, there's a covariance matrix in there, so it's going to contextualize it in terms of the typical volatility and correlations that we see.
Okay.
And then I'll also compare past observations to average attributes, and that's where the informative.
Okay.
So one's similarity, one's informative.
Okay.
It would be a you have and actually that goes into this slide. So this is an illustration of the Mahalanabis distance and how it accounts for the interaction. So your point, if you look on the side of the image dot, that would be a scatter plot of two attributes that are uncorrelated. So right, the middle is the average circle, the concentric circles, with different distances from the average. And any 2 points, or any point in the circle, have the same, in this case, Mahalanabis distance and equivalence. Where it gets interesting is when you have the two variables on the right, which here now have positive correlation and non-equal variances. And so now what was once the circle now becomes ellipses around the center. So anything on that ellipse that has the same Mahalanabis distance, they're not going to actually have the same Euclidean distance. So we highlight C and D here because C and D are the same Euclidean distance we know, but C is actually less distance from the Mahalanabis perspective because the two attributes are top, which would align with the typical relationship where D were opposite, and that would have been considered very. So that's Mahalanabis distance. Conceptually, the way that we're going to use it, and I started to, introduce this a little bit already, is now let's imagine we have 3 observations here. One is our current observation, everything's being characterized by 2 attributes. So what I'm going to do is I'm going to take, and I have 2 historical observations. So the idea is that we're going to measure each historical observation distance from today, from the current observation. And that's going to indicate similarity. That's one component of relevance. And then we also measure each observation distance from origin, average, and then those 2 things together tell me the relevance of each observation. So here, A and B equally similar, but B is more informative, more extreme, and therefore they're equally more relevant. So here's the map. So for these equations that you'll see, there'll be a couple of slides here. So you can think of observation I, the historical observation, J, the current observation, which will be the one that we're predicting. And each observation characterized by a set of attributes. So I've highlighted a couple of terms here. So the first term I've highlighted is the xi minus xj. This is telling me about the difference between each attribute and isolation. The second term of what we do next is then multiply them to inverse the covariance matrix. So to your point, that's going to be full sample covariance. That's how we contextualize how unusual something is, both in terms of the magnitude as well as correlations and patterns. And then the final term, the transpose of the first one I highlighted, is just going to collapse everything to a single number. So that's how we measure similarity. So again, 2 observations and measuring the distance between them.
Are xi and xj vectors?
I'm sorry, what?
Are xi and xj vectors?
Yes, yep. So it'd be a vector of attributes. Yep. So if you have 5 variables, or again, if you're thinking of this as 5 independent variables, then x would be a vector of 5.
Okay.
Yeah. Okay. Okay. Yeah. So it's multivariate. Yeah. So it's multivariate. Last point on similarity. Here we actually take the negative of the distance. So if you think of a distance as a measure of dissimilarity, the negative would be similarity. That similarity is actually going to be negative 1. Here's informativeness, basically the same thing, but here we're measuring everything relative. We're taking historical observation I vector, comparing it to the vector of average value for variables. So again, that'll tell us how extreme the observation is compared to the typical pattern. And then here's how the 2 come together to measure the relevance of that historical observation. So an observation's relevance is equal to its similarity to today, as well as the average of its informativeness, and then the informativeness of today, which is again the variable that we're predicting. That third term is including the informativeness of today. The reason we do that is because it centers relevance around 0, and that's going to be useful for purposes of
you know, you could easily see a scenario where it might be beneficial to wait a little bit.
Yes, but this ties directly to linear regression. So it would be kind of arbitrary to weight them differently. The way that we define relevance here, I'll show, is literally it's equivalent, produces an equivalent.
Well, this is
function.
arbitrary too. I mean,
Is-
it's averaging on this arbitrary thing.
Well, the way to interpret it, I guess, but I mean,
Okay,
this,
so
the
the
math
interpretation.
behind the interpretation, yeah,
Right.
yes,
But go ahead.
but the math behind this type stuff, yeah. And
Does
over
this-
time-
Does this have an information theoretic interpretation?
Yeah, and I don't know, so is this, I don't know if you heard me earlier, so yes, we think of, there's an information theory kind of piece here, where the idea is that we want to, the more relevant the more extreme an observation, the less probable it is, and therefore the more information it contains. So that's the kind of underpinning of our interpretation of this. A question?
Okay.
Sorry if I can't hear that well. Okay. Here's just an illustration of how this would work. So picture here, we have 8 attributes that we're looking at, E through H, doesn't matter what they are. X, T would be their values for today, like that vector X that we were showing earlier for today. And then this shows you what sort of values you would have. This would be taking vector that's being attributes historically, comparing to today, comparing to average, some of which is relevant, and this is what relevant. So as I said before, this is illustration. So now we're getting into forecasting and why this isn't arbitrary, and then how it relates to forecasting. So imagine then one prediction outcome. How do we use these bars to do that? So this, our definition of relevance is directly related to linear regression. And so it ends up that the prediction from a linear regression is equal to a weighted average of past observations of Y, or past outcomes, where the weight on that outcome equals the relevance of that observation. So rather than thinking of your prediction as, you know, a beta weighted sum of your X variables for today, it's actually just a average of historical outcomes where we weight them according to the relevance of that, which is a very different perspective. It's literally mathematically equivalent. I'll show it, and we'll see it numerically as well.
So what's the RIP?
Oh, that's relevant. So sorry, that's the sorry, I should be better with pronunciations here. Sometimes inside. So this is the relevance of observation I to time t, which is today. So I'm assuming I'm predicting today.
So we need a formula for RIP.
Yeah, it was that.
Oh,
I just had J there.
Okay.
It was generalized here so that t didn't have. This is relevance of kinetic observations. Here I'm saying today to time t. So yes, that's the relevance. So yeah, so what we're doing is we're taking, you know, all of our observations, we're calculating the relevance to today.
Right.
Then we're taking every outcome,
Right.
subtracting it from the average outcome.
Okay.
Then we're weighting those, you know, deviations, the outcome deviations,
Okay.
taking an average of that and then adding that.
So if we take the formula for RIP and we substitute it in here, yeah, if we go back to the question,
Yeah.
just remind me what RIP is.
So it's
No,
similarity plus
I'll
average.
have to go back and look at the
Yeah.
formula.
And I'm going to show another one where it expands it out.
Oh,
and
good,
shows
perfect,
how
perfect,
it
perfect.
relates to
Sorry.
regression. No, it's okay. And so I don't know, that might help. Yeah, so exactly. Yeah, that RIT is, I should be better with my. Yeah. So relevant, yeah.
So there's no assumption of
And so this is literally, I mean, this is what linear regression does. And so, I mean, it's a completely different way of thinking about it. But yeah, so yeah. Yeah, exactly.
kind of wondering if the relevance and something is happening, then I would really long time to say what was the end of that thing. It still have exceeds. Yeah.
Well, yeah, I mean, equated by extremeness and by similarity to that, with the prediction.
So I'm wondering the relevance factor, the property, the current one.
Do they like tend to overweight?
The relevance, then the factor, if I'm looking at today, if something happening,
Oh, it doesn't, I mean, it doesn't actually consider how long ago it was, but the similarity piece, the extent that no recent observations are most similar to that, that it would come through in the similarity part of relevance, but there's no actual, like, I mean, it doesn't care when that observation occurred. For all it knows, it could have occurred 20 years ago or a day ago. It's just looking at the X variables or attributes of every observation, comparing it to that. And that's similarity. And then also saying how extreme is every observation, and that's basically what. Well, I mean, I guess if the observations aren't like independent from today to tomorrow, and they're similar, then I guess it would, you would see them both be relevant in the next day. But to the extent that everything's independent, I don't think there should be any sort of cumulative effect. Yeah, so it could be, for example, let's say, so actually what these are actually a set of economic variables. And so your Y could be the return of a factor. So, well, let's say you're trying to predict the return, right? So it looks something like this. So you have your relevance, which is based on, in this case, the actual data, like a bunch of economic factors. Use that to discern relevance historically with all the gray bars. Then if you assume you have some sort of outcome that you care about, it could be the return of a factor of an asset of anything. Then basically your prediction is just that the average product is the gray and the orange.
Yeah, it looks like you were thinking about that. Maybe I'm wrong, but to the extent that the Mahalanabis Distance is a Euclidean measure, right? That it's multidimensional, but square root of square distance that way. If you're trying to focus more than one variable at a time, what you would end up with is a system of differential equations similar to what they used to call in the 1980s the state space model, where what you're calling the attribute vector is defining the state. And the relevance of the current state is, part of the inputs and how all the equations relate to one another. So if you were trying to, if you had, let's say, you weren't trying to forecast one thing, you were trying to forecast 8 things, you'd end up with 8 equations. And if they have variables in common, you'd end up with a system of differential equations, all of which are conditional on the current state. No, I had a checker, but I want to see that.
Yeah, I'll show you the math. So here's the math. I want to dig on the math. It would be, I mean, you could, yeah, you could substitute different, yeah. I think that the advantage answers and what we like about our approach is that we tied up kind of discussion. Yeah, you could read and persistence, and you could measure it and just have that in where we see value that, yeah, but where we see value that this flows directly from the interaction. So it's just for now, this is just a different way of doing it. So there's lots of interaction. I mean, there's lots of other things.
There's an infinite number of predictive models. So when you look at the machine learning discipline, it's infinite, right? And you can narrow them down by complexity and other desirability criteria, so forth. But we're making an argument here that linear regression starts from a baseline of simplicity and desirability in many respects. Interpretability, and also, unbiasedness and efficiency. But I mean, it is like, I mean, not to feel like it's wonder, but I mean, you sort of think of this as a baseline for expanding the approach to more nuanced or complex or powerful techniques, but
Yeah, maybe so this is just setting the stage for different ways we can work. From here, we can then use this perspective to improve it, make them slightly more complex, but not based on. So for example, I'll show Numerical for example, that basically allows us to introduce functionality. So rather than focusing on all of the observations, focus on just the relevant. And with that, effectively introducing conditionality, and it allows us to see that the partial sample would produce better predictions. So I'll talk more about that. But so this is just kind of like, yeah, maybe I wasn't clear. This is just kind of setting the stage for a different perspective on regression, and then from there we can think about ways to implement. Well, I didn't think that, yeah, I mean, this doesn't rely more on them being independent. Yeah, I guess maybe I was right. Yeah, it's not, we're not saying this only holds if I'm assuming that it's independent. Yeah, based on the serial correlation, and we need to yeah, so I will, yeah. So I can hop on the slide. This is the map. Yeah. So that's relevance broken out.
Thank you.
Yeah. So
Yeah,
so that's relevance broken out. I'll just explain. Yeah, and we have papers. Yeah, we have papers. So that's relevance broken out. So that's relevance broken out.
Yeah.
Next two lines, just kind of rearrange it and consolidate it to what you see on the third line. So that's just a really simple file.
Yeah.
So as you can see there, that's basically saying, today minus the average and the inverse of the historical observation.
Yep.
Simple. Plug that into our weighted prediction equation. Right. Previously we had that thing. Then this is just for simplicity, step 4, just for ease of notation, but this holds whether or not we do this, but this is now just assuming epsilon has 0 means, but the equivalence holds that it's not true. Rewrite this matrix, and then we'll notice the terms of data, so that then comes from the text. Yeah, so I guess that's what I was saying to you earlier, the way we interpret like 1/2, and the way we interpret things is one thing, but this math and this math is, this is how it's relevant. This is how you get it.
Well, what I just make up our comment, and comment on too, but it's really the intuitive skill. I think if you were to get like a room full of professionals or anyone really ask about predicting something and have a discussion around it, you probably spend a lot of time talking about historical events. So there's some numbers to the situation. extrapolating from.
Excellent point. Yeah. That type of event a long time ago is really relevant today, even though it was a long time ago.
Yeah, and I think that there's a lot, it's intuitive debate with historical experience that's relevant to deciding what you're going to predict in the future, what you're going to do, et cetera. And people are saying, well, what's the precedent for the inflationary time?
Yeah.
Is it relevant to look at such and such periods? But I think part of the problem that statistical techniques tend to use to talk about that, because machine learning is a little different, but it's not fully transparent. So most of the time we're talking about, well, I can't tell you, we can't talk about which historical experiences and debate and have data on historical experiences to look at. We can just say that the key statistic for variable 2 is significant. And I'm not to discount that, because that's valuable. No, but this is a whole way of manipulating the data that doesn't.
Yeah, no, I can see that now. This is getting rid of that time series embedded notion that today or yesterday was more important than, yeah.
So sort of it aligns to itself, and even when people look at event studies, and you talk about the notion of an event study is similar to what we're thinking about.
I did it the same way. Yeah, okay, right.
So anyway, I just want to put that out there. There's a thing that you ask people to predict something and discuss about it. My guess is they would end up talking about experiences, relevance, and less so like variables, although maybe. So anyway, this is almost a recalibration. It's a too little focus that the area want to do techniques to the what we're calling observations, the experiences.
Yeah. No, I didn't understand it at first. The more we go through it, talk about it, the more I think it's relevant. Well, not funny. Sorry. I had to get that.
Okay, sorry.
Yeah, no, that's helpful. I don't know if you guys want to, I mean, this is a numerical example.
I'm trying to make it relevant.
No, we actually do that all the time.
Go ahead.
I don't know if we don't really use it. This is just a numerical example. So how can we then now use this perspective to improve? So recognizing this equivalence, there's some interesting implications here. So what it means is that because linear regression is symmetrical, what it does is it assumes that what happens following non-relevant periods is just as important as what follows relevant periods, but it flips the sign of the outcome from the non-relevant period. Right? Some of our relevance values are negative. Now it's a weighted average of those, literally projecting and saying, I think what happens on relevant periods will happen again, and then what happens on non-relevant periods will happen again, but in the opposite direction, which is kind of a little bit of a funky logic that might not always hold. There's some sort of asymmetry in the relationship. So intuitively, for example, if you're trying to predict the path forward of a regression, of a recession, would you want to extrapolate from the opposite of high growth, or would you rather just focus on what happens following the previous recession? There might be reasons to believe that there's not asymmetry in those relationships. So this, once we kind of think this and assume should we then focus on relevant observations instead? That's going to give us more reliable.
The third point, I think, kind of summarizes one of the most important things.
Yeah. So exactly. So this is where we start getting into not just reinterpreting regression and happening. So should we just focus on the relevant observations? So we came up with this approach we call for sample regression because of that. So the idea would be that you still estimate relevance using all your observations, but then you filter and exclude or censor observations that aren't sufficiently relevant in forming your weighted average prediction. So that's the same prediction formula I said earlier, but here now you use a subset of observations that meet some relevant threshold. And there's just a scaling factor in there that prevents predictions from blowing up when you focus on predictions with large.
Are you going back on machine learning thing?
mean, there's
Or-
different,
or-
I mean, you could try and optimize the threshold, I guess, depending on, I don't think there is one optimal threshold, and kind of depend on the particular data and kind of do that. What we tend to find, so the reason I mentioned earlier that relevance is centered around here, that's just an natural threshold, so you could just kind of throw out anything that has negative relevance. Not that you guys need the illustration, because there's no illustration for that. You could just throw out anything negative. You could focus on be more conservative and say, we're only going to focus on the top 25%. What we tend to find is that it takes a lot of
Yeah, it's a little bit like Sample Regression concept. Yeah, it is, it's sort of, we use relevance as a continuous weight on how much to emphasize something, but it's also a practical visual.
right. Yeah, exactly. So we use it as a threshold and we use it as a, so you could do something more. Yeah, I guess we would. How do you set the subset of observations and how do you then do that? For this, we just create them. Well, there's three and
It could be binary. It could be categorical.
oh, I see. Yeah, they can do that. Yeah, you can have categories. Oh, sorry. Yeah, I hear. Yeah, it doesn't have to be. Yeah, it could be categorical.
That's another.
It can be binary. Yeah.
This is the reason why we want to piggyback on linear regression. Everyone, everything you think is okay for linear regression is also okay for us as a baseline.
But it's also the antithesis. It's like you have to merge.
We can relax.
Yeah. You have to kind of merge the continuous item or the pointers along with the cross section. And it's kind of what I'm thinking of trying to do. But I'll just look through that. But I'm sorry, keep interrupting.
No, it's fine. No, that's the whole point. That's probably easier for in person too. So, yeah, I mean, here we do predict, well, so we predict the bounds. Percentage of it. Yeah, I'm actually gonna show that. I know it's not finance, but it's an intuitive one, so I'm just gonna show that one. I guess one point on partial sample. Well, actually, no, we have a real estimate.
Oh, of course.
Actually, I don't show it, but we did it. Yeah. Before? No, truly, yeah. Yeah, we ran a couple, I'll show you. We ran a bunch that were out of sample in the sense that they, none of them had forward-looking information, but the 2021 we actually ran on. It was truly So one of the things I'm going to be sure to cover. So that fits very well with the framework. So if you think of it, so we can come up with a measure of fit and confidence for a single prediction. So if you think about the single prediction perspective, right, there's actually many kind of individual predictions that are underlying applications. So each observation is effectively passing some vote, and that vote represents relevance and its outcome. So what we can do is we can look at effectively the alignment between relevance and outcome in the observations underlying the prediction, and that can tell us how confident or how strong of a fit there is in the data. So In other words, it's basically saying on my relevant observations, do they all have similar outcomes? Do they tend to agree? And if so, you would be more confident in the prediction. So we actually have a measure called fit that does just that. So it would vary between 0 and 1. The analog, if you were to do this across every single prediction and look at how well predictions across the whole model, how well they predict actual outcomes, would be the R-square. You can actually do something very similar to a single prediction that just says how well do the outcomes and relevance align underlying this prediction. It varies between 0 and 1, with 1 indicating perfect alignment, meaning everything seems to agree in terms of the more relevant observations tend to suggest a similar outcome, as opposed to 0 would indicate that everything kind of looks like this. There's no real consistency in what the underlying observations are. So that's really trying to go back to the balance. Another way to do it is, as I mentioned, you have all these individual predictions underlying, rather than looking at the relevance, or to see the alignment between the relevance and outcomes that are fueling these predictions. You can also just look at the variance. So it's definitely yeah. Yeah. We actually did that in the original presidential. I don't have it. I know at one point I had a ton of results in here. Keep saying I have things that I'm not showing, but really do good things. I just don't have it. I just don't have it here. One point I wanted to make, and no one asked this, but partial sample regression is not the same as if you were to just run a new regression on a subset of the relevant observations. So sometimes some people have to say, okay, why don't you filter down your observations and just run a new regression from that data set? The reason we don't do that is because relevance is within the context of the other observations. So what we would effectively be doing is if you reran a regression on a subset of relevant observations, you'd be redefining relevance, kind of forcing our data to think some of those observations or model is not relevant, and it would kind of screw with what we want to be doing. So it's different. And then we have a bunch of applications around predicting asset return, platform correlation, and then selections. I keep reading this part, but I'll come back to it. I know. Geez.
We're gonna lose another one next.
Okay, well, I'll finish up quick. I'm almost done.
Right.
So this shows, so this is the, this is the US elections model. The line is not showing the result. Okay, anyway, so this shows for 2000. We did this last summer. We ran it for the prior 5 elections at that point in time, and the upcoming 2020. And did a good job. This is just another point. Interesting to just visualize the data setting of it too. It's just interesting to be able to visualize the relevance, the observations, feeding your predictions. That's another benefit, and that is some of the fit stuff and everything that we talked about. We're almost done. And then this is just relating to the event studies, which Dave mentioned. So long story short, of traditional event studies, identifying events, recording subsequent paths of variables, finding them to time 0, and then calculating an average path as your prediction. Basically a variation of partial sample. So, or partial sample if you were to relevancy would result in a similar thing. So I can go ahead and edit that. I think I'm losing people's attention. Yeah, we can edit that. Yeah, no problem. And we have papers that cover, yeah, absolutely. Yeah, so we have papers, and we've been doing more stuff, Mark, Dave, and me, besides what's even covered in the papers. So we'll have more stuff soon to share where just expanding upon the full observation-based perspective, and there's a lot of value in how you do that beyond just production. So we have other stuff. That will be
something that is relevant in the 2 years relevant in the future ago. They have some aspects.
Well, it might help to think of it not as a time series.
Yeah, no, that I think is key.
Because it certainly applies anywhere you can do regression, But, you know, like, for example, we've thought about a good example of like health outcomes, because we have a database of 100,000 patients that have different health, you know, measurements, all their characteristics, right? And then what you want to predict is their outcome, right? So whatever. So there, you know, it's a bunch of independent, like, correlated observations. And what we're saying here is,
What is the example of that? You made the example, just thinking about that example, someone someone had an accident, and then maybe they had a fall after the accident. So
I guess I'm just thinking about a case where there's no temporal data at all. It's just, you know, this cross-sectional attributes of a person's health when they visited the doctor, and then something about the next year, whatever, some outcome.
Just drop the T of the observation.
Yeah, I mean.
Well, that's why I usually have the J in there. And then we made it, because it's any two observations, so it could be you could be comparing 500 firms and you're identifying for a given firm with a set of 5 various attributes. What are the relevant other firms in the sample? So yeah.
But I guess to some extent, it really depends on what it is that you're trying to predict. And this would be very valuable in adding something to the criteria. But if you want to just confusing your criteria,
But I think a good example might be, you know, if you're trying to predict what's going to happen in the next year, you can say, well, recent data is not inflationary, but it has all these other attributes that are reminiscent of today.
Yeah.
Then I need to weigh that against the inflationary period from 40 years ago, but it's dissimilar to what it was. And I think what you want is some intelligent balance of those things,
Yeah.
because, you know, both are partly relevant and partly not relevant. And, so I guess the point is that the data could suggest in that case that recent data warrants, you know, being overweighted. But it may also suggest that some different thing because of this striking similarity to whatever is happening. So all of a sudden, the presidential elections looked at 100 years ago to some election that, you know, statistically speaking, using the data that put into it was more relevant and had similar patterns of political alignment and non-alignment and stuff like that.
But it's kind of same thing as just taking a dummy variable and turning it into an uncertain expression.
Well, what's the double variable?
Well, the dummy variable is an event that happened in the past that, you know, if you were doing it, I think it's a model driven, but we're not going to have a coefficient on that. But I'm trying to think of it sort of a conventional way of, you know, a way that people might have been thinking about including data.
Oh,
Yeah.
You sort of force it to include it
By saying
Yeah, right in
today,
there.
yeah.
but then it's sort of exogenously determined.
Correct.
Right?
Yeah.
It's not part of the synthesis of the data.
Correct.
Yeah. But I think it's interesting, it was definitely interesting to us to learn that linear regression can give you assessments.
I hadn't read it, right? I think it's a great valuable thing.
And which, you know, is not so different than the assessments that people make all the time about, well, you know, this basketball player is like that other basketball player, you know?
It's got intuitive.
Yeah.
I mean, intuitive relevant?
But it challenges the people are very trained to think of things in terms of many variables.
I think of all the stuff, all the econometrics, I read everything well, and, you know, next to this is defining it, it's always the same, always the same. And then it is, great.
Thank you.
Good luck. Thank you. Good job.
Yeah.
Yeah, I mean,